Welcome to another lecture video of OpenStax Astronomy. Here we'll be covering Chapter 4, Earth, Moon, and Sky, and this will be part 1 of 2 lecture videos. And we'll go ahead and begin in 4.2 as the definitions in 4.1 have already been covered. So let's start off with a thought-out question here in Long Beach. In what season is the Earth closer to the Sun? So think about your personal experience when it's hot, when it's cold. What season do you think we're closer to the Sun? And a hint here is think about birds flying south for the winter. Why do they fly south? When it's summer here in America, is it summer in Australia? So if you thought of distance, this is a common misconception that the seasons are caused by distance to the actual sun. And really when we're at aphelion and perihelion, so our closest and furthest point, the difference is only about 3%, about 3 million miles, which is a very, very small amount. If it was in fact distance that was the reason for seasons, then it would be summer all over the world, and then it would be winter. But different hemispheres have different seasons. So distance alone does not matter. The seasons are actually caused by the axis tilt. The Earth is slightly tilted on its axis, 23.5 degrees. And so as we orbit around the sun, that slight tilt has direct sun rays, and then some are slightly off. And that little that slight amount of angled light is enough heat to create the differences in weather temperatures. So here's an image where we see direct sunlight, or almost direct, and we could see on this first image here that if you have some light rays that are coming almost direct, the area that it will cover is a certain amount. And if the light is angled, that area or the amount that it covers tends to be spread out further. So when it's concentrated in one small region, you're going to have more intensity and it's going to create more heat. If it's more spread out, then it's not going to be as intense. Also, the path of the sun. So how long it is out. The sun's altitude also changes during the seasons. So in the summer, we see that the path of the sun tends to be higher here, and it's going to be out longer. As opposed to winter, the path is going to be shorter here. It's not going to go up as high, and it's not going to be out as long as well. So summer, first day is what we call the solstice. That's when it's at its highest path. And then the lowest path is the winter solstice. The equinoxes, it actually rises and sets due east and due west. And it will be exact sunlight for 12 hours, and then the sun will be down for another 12 hours. So the day and night are exactly equal. So throughout the year, this path tends to change, and it'll go back and forth. And so that's how we know when it's the first day of summer, first day of fall, and the other seasons. These 4 points are marked on our orbit around the sun. So when we are on that major axis in the ellipse, and then also on the minor axis. And so, in fact, we are actually closer to the sun during winter. And we are furthest away during the summer in the northern hemisphere. Along the Earth, we see these kind of imaginary lines. Well, the equator is what divides the center here. There are a couple of other latitude lines. So the Tropic of Cancer, which is slightly above here, on the first day of summer, that would be getting that direct sunlight, where it would be the sun would be overhead. And the Tropic of Cancer. I'm sorry, the Tropic of Capricorn, which is below the equator here, is where we would be the first day of winter. And so again, those light rays being slightly angled. The seasons at different latitudes are also more dramatic the higher you go. So seasons change, they're more extreme. So Vermont has longer summer days than Florida because it's further up. The Arctic Circle, latitude about 66.5 degrees. During summer solstice, the sun remains above the horizon. So we talked about stars that are circumpolar, that never set or rise. So imagine that on the summer solstice, the sun will remain above, so for more than 24 hours. And actually at the poles, so north and south poles during summer and winter, the sun never sets or rises for 6 months at a time. So imagine that, complete darkness for months at a time, and then complete day for months at a time as well. Very extreme changes in the seasons as you go up in the latitudes. We've talked about this before. Section 4.4 is looking back at why we study astronomy. And currently we have the luxury that it's for curiosity. However, before it was really for keeping track of time and the seasons. It was really mainly for the calendar. So astronomy is the oldest science, and we have to keep track of time. We need to know when the rainy season is here or when the dry season is here, when to plant crops, when to deal with our agriculture. So keeping track of time was an essential tool. And so what did ancient civilizations achieve in astronomy? Daily timekeeping. So again, the Earth rotates on its axis. When it spins around once, that's what we call a day. Tracking the seasons on the calendar. So as we orbit around the sun, that's an entire year. But when we're at special points in that orbit, mark the different seasons. The moon orbiting the moon cycle is roughly about a month as well. And that is where the term moon comes from, very close to month there. Monitoring planets, stars, predicting eclipse, much more, but really had a fundamental idea with the seasons, keeping track of time. This is Stonehenge, probably familiar with this, in Europe. And so 1550 BC, this is a way to keep track of the motions of the sun and the moon. So kind of calendar. And so different times of the year we could figure out, what these different seasons would be. The strange or the mystery behind Stonehenge is that these type of stones and rocks are not found anywhere near the site. They are at quite a distance, so it's puzzling how these rocks were actually brought here and then stacked. This is a Mayan observatory in the Yucatan of Mexico here, 1000 AD. So even these ancient civilizations were studying astronomy so much that they already had buildings dedicated to them. This was in Egypt here, and this is more of a keeping track during the day here. This now resides in the Vatican, but looking at the shadow throughout the day, you could see it kind of resembles a clock here. And AM, PM, post meridian and pre meridian. So if the meridian, again, that imaginary line going from north to south that breaks up the sky in the east and west hemispheres. And so, depending where you were at, right, is that post meridian, pre meridian. So that's where AM and PM comes from. This is an old Aztec temple here, 15th century. And so this temple and really the whole city here was built so that it aligned with the summer solstice. So at certain seasons, the sun would line up and they would have huge festivals in the courtyards, and their development, their architecture was designed around that. Here in the States, in New Mexico, about 1050 AD, here we have where right through this hole here, sunlight enters and this dagger type feature lines up perfectly there, again on the solstice there. So another way for them to keep track of seasons. Machu Picchu in Peru, 8,000 feet above sea level here in the 15th century. Again, the structure is aligned with the solstice. And you could see the huge courtyards again when it's a change of the seasons. Again, rain bringing water for crops resembling life. All of these, a lot of these old civilizations look to the skies to guide them. And again, huge buildings and cities were developed around the solstice and other celestial events. Scotland, 4,000-year-old stone circle. Not only does the moon have, close to that monthly cycle with the phases, there's also a 18.6 year cycle, and they were aware of this. So this huge stone circle here, keeping track. Again, now they would not only have to find a pattern, track it for a lot, for a long period of time, and then build a structure. So they were studying and observing the skies and the heavens throughout the world in many, many civilizations. In Central Africa, in about 6500 BC, they use the phases of the moon. So here we have a crescent, and the angle changes very slightly. So you could see that here in the middle, it is completely flat, kind of like a happy face there. But it changes. It starts veering off to the right. And prior to that, it veers off slightly to the left. And so by looking at the angle, we could see when the raining season is going to start. So just by looking at the phases of the moon, and that told you when to plant crops, so when the rain was coming, and then when to harvest them, right? When we came right across the dry seasons. A cave in France. Here we have a painting, 29 dots, which suggest the lunar phases there. So roughly about a month period there, resembling the phases. We have records in China, 1400 BC, where they were, again, not only looking at the night sky, but taking records of supernova explosions. And so looking at the heavens, not just for basic time telling, but also for other phenomena that were being observed. Polynesians in the South Pacific here were very skilled in celestial navigation. This is more of a ancient GPS system where they would hold this up to the night sky, align it with several stars, and then be able to travel, so jumping from island to island. So the objects or the planets that we could see with our naked eye in ancient times were Mercury, Venus, Mars, Jupiter, and Saturn. Those five, along with the sun and the moon, create the 7 days of the week. So the planets move fairly quickly compared to other objects in the night sky, and so they were very noticeable. And so here we see that the 7 days of the week are in fact attributed to those seven objects. So had we been able to see other planets with the naked eye a bit easier, perhaps we would have had 8 days or 9. But Monday, fairly simple, as the moon. Sunday as well with the sun. Some of these not as obvious, but Friday is Venus, and Viernes, perhaps in Spanish, makes a bit more sense there. But again, time or the days of the week are attributed to the seven objects that we could see. And so keeping track of time was a huge endeavor there. And so the Julian calendar was off about 11 minutes per year. And so by 1582, those 11 minutes added up to about 10 days. So it was about 1582 when we adopted, or when they started adopting, the Pope Gregory calendar. And so Europe adopted that in 1582. And so 10 days were lost at that point. England and America didn't adopt that until 1752. By then, 12 days were lost. And then Russia, not till 1917. That's not that long ago, right? Only about 100 years ago or so. And so by that point, 13 days were omitted. And so our current calendar system is what we consider the Pope Gregory calendar. Okay, so this concludes the first part of chapter 4. We'll go ahead and continue the other sections in the following video.